My name is Erica Muskowski. I'm a research analyst at the New York Fed. And my team, the DSGE team, released a package called dsge.jl in December, so that's what I'm going to be talking about today. But before I keep talking, I have to do the sort of standard Fed disclaimer, which is that everything I'm talking about reflects my experience and not an opinion or endorsement of the Federal Reserve System or the Federal Reserve Bank of New York. So I've said the letters DSGE a lot already. What is a DSGE model? It stands for Dynamic Stochastic General Equilibrium, which is a lot of big fancy words. And what it really means is that we have this structural model of the macroeconomy that's useful for four main things. First, forecasting macro variables like GDP and inflation, interest rates, all that good stuff. Understanding the forces that drive the economic outcomes that we observe. So, for example, what is the reason that we see low interest rates? Or what is the reason that we see inflation at the level it is? And those are questions that we can answer with a DSGE model. It helps us conduct monetary policy analysis. So, for example, if we wanted to see what would happen if we used a different interest rate policy, that's something we can do with the DSGE model. And we can also analyze different kinds of counterfactual economic scenarios. So if we wanted to know what would happen if there was a global credit crunch, for example, we can analyze that with the DSGE model. Or if we were, before Brexit, we were like, well, what's going to happen if there's Brexit? That was something that we could analyze using the kind of model that we had. So this is a model that we use. My team works with every single day at the New York Fed for both research and for policy purposes. So we produced this package called dsg.jl. What does it do? It mostly just estimates and solves DSGE models. We can use it for forecasting. So it does all the things I talked about. And it has four main sections in terms of the code. The first is it prepares data for us. My colleague Micah Smith wrote a different package called freddata.jl. So you can make direct queries to the Fred database, which is the Fed's main database for economic data. And we solve the model and estimate its parameters. And then the thing we're currently working on right now that's not yet public is the forecasting step of the model. So if we wanted to forecast the future path of GDP growth, that's something that we hope to have available soon. And then plot everything so that we don't have to look at giant tables of numbers. It's on GitHub, yeah. It's on GitHub. And then using DSGE looks something kind of like this. It's very straightforward. Once you've defined your model type, which I'll talk a little bit, then you can configure. It has configurable settings, so you can change, for example, the vintage of data that you want to use to estimate the model. You can change how far out you want your forecasts to go, things like that. And then you just load the data and estimate it. Once we add forecasting to the model, we'll have just another line that says basically forecast the model, and that's it. So it's, from our perspective, very, very straightforward to use, which is important to us because we do this kind of stuff all the time. And the package tries its best to provide functions that are as model agnostic as possible. So we know that DSGE models are a very specific kind of macro model that not your average person is just running all the time. So we provide a lot of what we think are useful functions in a model agnostic sense. So GenSys is a model that's used specifically for solving rational expectations models, but we also provide the standard Kalman filter, which is a very common state space routine, some functions that are used for computing Hessians of large matrices, things like that. And then we do have a couple of specific functions. So we use the Metropolis-Hastings MCMC method. That one does happen to be model specific, but we try to be as model agnostic as possible. So why are we using Julia at the New York Fed is probably a fair question to ask. So the DSGE team has existed at the Fed for about 10 years. And for most of that time, although there are other software, there is software out there for solving DSGE models, we developed completely our own code base in MATLAB, primarily because the tools that were out there just weren't flexible enough for us. We needed to be able to customize basically everything, and so there's a package out there called Dynair that we just don't use because it's not flexible enough for us. In September of about 2 years ago, the team released the MATLAB code that we were using in a zip file on on our blog. So Liberty Street Economics is the research blog of the New York Fed. And a few months after that, the Quanticon organization, which is an organization that promotes the use of open source code in economics, it's headed up by John Stochastic and Tom Sargent. They approached our team and they said, we would really like it if you would make your model open source, if you could put it in an open source language so that anyone who wanted could run it. And to us, that was a great idea because first of all, MATLAB, we were like kind of running up against the what was possible to do in MATLAB. One of the things that my economists have been wanting to do for a long time is start using a nonlinear model. Our model is very linear. It has one nonlinearity. But if we wanted to add more nonlinear features, we just couldn't do it in MATLAB. We didn't have the performance that we needed. And our code base, because it's 10 years old and has been administered by about 10 or 12 different RAs like me, it has become extremely unwieldy and terrible in lots of ways. And so we just needed to do it basically over again. And it was important to us to be able to make the code free. We thought that if we had gone to all the trouble of making it public, we might as well make it free so that anyone can use it, and you didn't have to have proprietary software like MATLAB to do it. So then in December, we released the estimation step of the code on GitHub, and then we released the data step in June. All this is going simultaneously with our policy work, so it's unfortunately not as fast as we'd like it to. But we should be coming out with the forecast very shortly in a couple of months, and we're really excited for that. So we've been putting a lot of work in that recently. Why are we using Julia? Our initial reasoning was not super good. I will own up to that right now. When the team decided to go with Julia, we mostly picked it because it was relatively easy to move to Julia if you were coming from a MATLAB background. One, indexing was important so that my economists could read our code and understand kind of like what was happening. That was basically the main reason why when Quanticon approached us, we decided to go with Julia over a different open source language like Python. But fortunately, hindsight is 20/20, and we have a lot of really great reasons now why we use Julia. Primarily, the type system and multiple dispatch are two things that actually really support economic intuition. And that was kind of the most amazing thing to me when I started working with Julia, is that, wow, like, programming language features can support economics. That's so cool. So I'll give an example of that shortly, like a really simple one, but I think it's really neat. And then, of course, we rely on the JIT and the compiler to do the heavy lifting for us. But with that in mind, I'm just going to show you a couple of summary stats. Our code is not exactly a direct port of MATLAB because we are trying to make it better and more organized and that kind of thing. But just to give you a sense of how much easier it is to manage our code, we have about half the number of lines of code in the estimation step as we did in MATLAB. And in general, our performance overall is about 9 times as fast as it was before. So here, smaller numbers are better. The top table has code that's mostly comparable between MATLAB and Julia. The bottom one has pretty substantial redesign, but basically when we run our Metropolis Hastings sampling algorithm, we solve the model, which is using this routine solve. We do that about 100,000 times. So that function matters a lot, and it sped things up for us a lot when we translated it to Julia. And another big reason that we have this, like basically the main reason that we have such a huge performance improvement is that we're using types all throughout the DSG-AL code base, which is not a surprising thing to say in this room, but it is a very surprising thing to hear if you're an economist and you don't know what types are. So we had to do a lot of, we actually ran a seminar at the Fed, like what are types, like what is Julia, how do you define types, and it was like really exciting to be able to talk to people about how you turn an economic concept into a data structure. So that was a neat thing. So we can encapsulate all of the features of like an economic object that we think about in economics into one data structure. And one example of that would be the model itself, which I kind of threw up on a slide earlier. And another example is the model parameters. So the parameters of the model are something that basically the entire model can really just be synthesized into a mapping from parameters into a set of matrices that govern the transformation of a system over time. And in particular, the system we're interested in is the US macroeconomy. So, we have a mapping from our set of parameters into a set of equations that tell us how GDP evolves over time or how inflation evolves over time. We are Bayesian in our group, so we consider theta to be a random variable. That means we impose a prior on it. It also has a number of other things. So we might want to enforce the fact that a parameter has to lie between 0 and 1. We might want to fix that parameter at a particular value and say that, we are very, very sure that this parameter has this value. And we want to have some utility stuff, so we want to be able to print that parameter to a file and have nice tables without too much work. And so we can throw all of that into a parameter type. And here I have an example where, I don't know if you can see this under the table, but we basically just define a parameter called alpha, which is the capital share in our economy. And it has a value, and it has bounds, and it has a prior, which is normal in this case. We are not fixing it, and we have a label for it and all that nice stuff. And then this is the part that I think is really cool, which is that multiple dispatch is going to support our economic intuition when we're thinking about the model and we write the model down in code. We want, in this package, we want it to be as easy as possible to go between the math that we write down on paper when we're developing the model and the code that we need to run that model. We don't want to be trying to guess well, this parameter is called alpha here, but I can't have alpha in my code, so I have to call it alp. And then, when you scale that up to 85 parameters, you're trying to remember what your parameters are called and how you go back and forth between the two. So in Julia, Unicode makes it easy to do that, but we also want to make it easy to write down equations. So here, I have a parameter, it's called alpha. I want to add 1 to alpha. Even though alpha has lots of these other fields in it, naturally the intuition when I say I want to add 1 to a parameter is I want to add 1 to its value. So in Julia, I have a one-liner function that allows me to extend the plus operation to add to a parameter. And this is a fairly standard and normal thing to do. But what's not so standard and normal is I want to be able to add 1 to alpha, or flip it the other way. So I want to be able to add alpha on the right. And this is actually a non-standard thing. In most programming languages, you can't do that. But in Julia and in any language with multiple dispatch, which I guess there aren't that many, you can do that extremely easily. And it's just one extra line of code, and you're done. And so this is important for us because we define the equilibrium conditions of the model, which are the equations that govern the system's evolution, all using this syntax. So everything that we do in the model kind of looks something like this. So here we have a production function. It's already log linearized. And we have 2 parameters in there. We have phi and we have alpha. And it's really easy for us to just write down an equation. It looks exactly like how it would look if we wrote it up in LaTeX or if we wrote it down on a blackboard. And that makes it a lot easier for us to develop the model and then just solve it and run with it. So obviously moving to
Just 2 quick questions. The first one, I'm not an economist, so I'm just interested in that non-linear.
Yep.
Those non-linear parameters that you use, the definition of those, number 1. And then number 2, a bit softer, which is, we might get into this, but was there a challenge getting, the other departments of getting people to buy in to this, the fact that this was actually going to produce the right numbers at the right time and there weren't going to be errors or issues? That's a big question for a lot of companies, especially with capital.
For sure.
Just those 2.
So yeah, there were 2 questions. The first question was about whether, what sort of the nonlinear approach would be. So the entire model, which I didn't write up here just for the sake of time and also not to bore you to death, but the entire model is a linear model. So that means that we have basically a linear set of equations that define the economy, basically, and how things transition from one period to the next. And in an ideal world, we don't think that the world is actually linear. We just think that's an approximation of the real world. We'd like to have some curvature in there. There are techniques for that, but they're relatively computationally intensive. So that's what I mean when I say nonlinear. So like if I go back to this guy, that's a linear equation.
Just using,
Yeah.
more than just using variables and parameters that are non-linear, but the equation itself.
The equation themselves, yeah.
Not just like a multiplication.
Right. Yeah, so the nonlinearity applies to the equations. Yeah, for sure. And then the second question was about getting people to buy in to using Julia. The way that my group works is basically the only people that we really had to convince was the two economists that I work with directly. And as long as we produce results that are consistent with our MATLAB results, that's all that matters. We are in a lucky position where no one relies on our code but us. So we are modular in the sense of like in the organization that is the New York Fed, our team can substitute out our software and not affect anyone else. That being said, we are like slowly but surely convincing other people to start using Julia. So like one of my friends on the floor who also does macro, but he does more nowcasting stuff, has started exploring with Julia. And so we hope that more people will start to use it. But right now, we're the only ones using it for production work. Yep.
What's been some of your biggest challenges?
Yeah, so excellent timing. So,
Okay.
yeah. So
Read the slide.
Are you using Julia or Julia Pro?
we're using Julia. Right now, we're just relying on open source. Part of the selling point of using Julia was that it would start costing us less to operate, but we'll see what happens as we go forward. So somebody over here asked a question about challenges in development while using Julia. My biggest challenge, personally, and my personal biggest like wish list item for Julia is I would really love to have an interface. I think like our whole concept is basically based around this idea that we have a model, and if we're given a model that's constructed properly, we can do the entire, what my economist calls the whole shebang on it. And right now we have no way to enforce the fact that models have to be constructed correctly. So an interface would be really helpful for that. Another big challenge has been the maturing package ecosystem. So when we started out and we implemented a Kalman filter, we were first looking around to see if there were any other Kalman filters out there, and there were probably like 4, but none of them really did what we wanted them to do, so we implemented another one, and now there are 5, and kind of we can see how this might go. And another thing when the package ecosystem is changing a lot, there's a lot of churn, is that some packages will just sort of fall away, some will become really popular, but you weren't using them when they got started, and some of them are just really lacking documentation. So one of the things we've been working on in the forecast step a lot is we're really relying on distributed arrays. And the distributed arrays documentation is like not fantastic, so we've had to spend a lot of time like figuring out how distributed arrays work. Which could have been a lot easier if like there had just been a little bit more documentation.
I didn't know that anyone used that stuff.
We do, a lot. We really need it. We submitted a pull request, or not a pull request, a big issue, but basically it has we wrote the documentation. Like someone should just take it, incorporate it. Okay. So anyway, so we like them. We like that stuff. And similarly, there's like non-autonomous Stack Overflow, but this is a problem that will solve itself in the future. And lastly, another big challenge has been using most of the time using the linear algebra libraries is like a breeze, totally fantastic. Sometimes there are discrepancies between the underlying LAPACK algorithms that are used in MATLAB versus used in Julia. And since our entire workflow is basically can we replicate our MATLAB code, sometimes that can cause some issues. So like this showed up in the SVD algorithm, and figuring out how to get around that can be a little bit of a challenge. But that might just be like idiosyncratic to us.
I should add that we use a faster SVD algorithm.
Yes, there are benefits, right? Like it's faster and stuff, but it can make it hard to like.
So slower moving software usually uses older versions of LAPACK and hence has different algorithms under the.
Yeah.
Just for the audience.
Yeah. No. Do you need me to repeat that? Okay. Cool. I don't know. I just want to check. Okay. So ongoing work as we're working on the forecasting step, which I think is like the last big piece. Plotting is going to be like hopefully really simple, and we're excited to use like all the proper plotting infrastructure that's out there. But the forecasting step, once that's done, we're going to have like everything in place, and it'll be really exciting. And that hopefully will be done in the next couple of months. Long term, we'd hope to get in some of these nonlinear solution methods, like I talked about earlier. New optimization routines. So one of the things I've been messing around with recently is using simulated annealing instead of CS-Minwell, which is our current optimization routine. And what we'd like to do is use some combination of the two so that we can like kind of hop around our distribution, our parameter distribution, posterior distribution, and pick out like hopefully where the global mode is, and then run gradient descent algorithm to get us to the mode. And then we'd like to try to use some new estimation routines. So we had 2 interns this summer who were working on sequential Monte Carlo, and hopefully we'll have that up and running soon, which is just a different sampling technique that's has the potential to be a lot faster because it can actually be parallelized as opposed to the Metropolis Hastings algorithms that we use right now. And we're pretty sure there are probably better ways to do everything. So if people do use this kind of stuff, submit pull requests and issues and stuff. We like to hear from people. And that's basically it. So these are all the people that I basically have to say thank you to, which is my team at the Fed, and then all of our collaborators at QuantEcon. So Spencer is here. He like really helped us get off the ground when we had no idea what we were doing. Yeah, so thank you, and yeah, check our GitHub.